The difference between them will produce output. Okay. Now, for efficiency, this is the output, as I mentioned, divided by the heat or the energy input. And energy output here is the difference between input and output. And you know from thermodynamics that heat in over temperature hot equal heat out over temperature cold. So we can write temperature cold in this way. And substitute here and simplify. We go to what we call it Carnot efficiency. What it say? Temperature difference divided by hot temperature is the Carnot efficiency, which is usually small. Now, if I want to drive it in another way by using per kilo mole basis, okay, I will say that the energy or enthalpy of the turbine equal mu when I'm talking about gas, because at the end we have vapor, is mu times H minus out, or we put mu as output. Here mu is the permeability of the gas. Okay. Now, when I want to find the difference between H in and H out, okay, then it will be integration of heat capacity with respect to temperature between in and out. And we can write it in this way. And since W is mu H in minus H out, okay, we can put this part in space in front of this part here, as you can see. Now, multiply and divide by Tn. This one will be Carnot efficiency. So this tells me that the energy produced is mu C Tn by Carnot efficiency. And Carnot efficiency, as I mentioned, is small. Now, it's worth to mention here that the temperature, if it is increased, the difference in temperature between them, it will be good to produce a huge amount of energy, increase the energy, increase the efficiency, reduce the cost, and the depth of the to get the cold temperature, if it is reduced, this will be reflected on the cost also and the efficiency also. But from the other side, Prof. London from Stanford University found that the minimum water consumption occur when temperature difference is delta T over 2. You may say, okay, temperature, water consumption here is not an issue because we are in the ocean. It's not similar to other system. Consumption of water is, let me say, is a problem. No, I know, I get it, but what happened is the consumption, if it is increased, we're talking about increase the area of the heat exchanger. And don't forget that most of the cost of this system is paid for the heat exchanger area. So if I want to write the flow rate, V0, flow rate of warm water, it will be 1 over 2 delta T over 2, because we say it is delta T over 2. So it will be 1 over 4 CV0, okay? And the power, if I substitute in the power, this part, okay, this part will be multiplied by delta TC over TH, which is Carnot efficiency over 2, because we are talking about the minimum water consumption again. Now, if we assume the flow rate for the cold and warm water is the same, then the average will be V total over 2 equal V naught, or 2 V naught equal V total. So if I substitute it, we're approaching here. Now I simplify, okay, I got this formula, which tell me that the power of Otic related to the difference in temperature and the flow rate. Increase the flow rate, increase the difference in temperature, increase the, let me say, power production. If I compare it with the power production by hydro, okay, so we can find that for small temperature difference here, temperature hot is 296. So if the temperature difference is around 20, okay, then, and I equate the hydro power with the Otic power and simplify, we will find this formula. This formula relates the difference in temperature with the height, difference in height between low and height of the hydro. We will find that hydro plant, which have height 34 meter, okay, is equivalent to the production of otic with 20 Celsius temperature difference. And don't forget, 34 comparing 34, I mean hydro plant produce around 400 to 500 mega. 20 difference producing this amount, 300 to 400. Most of the cost is definitely consumption is paid for the heat exchanger, which is expected to be large, in the range of 400 to 400 by 400 or 500 by 500 square meter. Yeah. Now, let's take design and discuss it. Have a look. Let's assume that I will read the example here. We have a closed cycle. The working fluid is ammonia, as you can see, and the temperature at the warm side is 18 point something, and the warm water flow rate is given to you. Okay, this is on the warm side on the heat exchanger. And on the water side of the heat exchanger, you can see that it was 26 reduced to 25, so differences between them is 1.36. Now if I want to calculate the Pn, I will multiply the flow rate by heat capacity of the water by delta T. As we know, we got this number. Let me have a look at this number. It's talking about 1877 around megawatt hour thermal, which is huge, 1.8 giga. Okay. Now here is the details figure. You can see this is heat exchanger on the warm side, on the cold side, and the warm surface temperature 26, and the other sides go to 25. So we have reduction here, and transfer to the ammonia it will be 23, and the same thing for cold on either side of the heat exchanger, transfer to 11 point something, and pump here to pump the ammonia to the turbine. Now, if I want to find the Carnot efficiency, definitely on the ammonia side, I will find the difference between temperature hot and cold divided by the hot. I added definitely 273, okay, in Kelvin. And he told me in the example that 90% is the electricity part, okay, its efficiency is 90% of the Carnot efficiency. I multiply by 0.9 mean. And further for that, 28% of the total power generated will be consumed in the pump. Breakdown of this is here, as you can see here: condensed pump, reflex pump, warm and cold water pump. Altogether, 19.55 mega is the consumption in these pumps. Now, to calculate the electric power generated, I will say, okay, the thermal energy multiplied by Carnot efficiency by the efficiency of the generator, it tells me around 69 megawatt electricity. I subtracted here the consumption inside the otic system for the pumps, which is 19.6 given the question. Around 50 mega is what I produce. For that, when I calculate the efficiency, 50 mega is the final production, and this is the amount of thermal energy extracted from the surface of the water. You see here, talking about 2.6%, very small, but as I mentioned, it's cheap, 24 hours, 7 times a week, 7 days a week. Now, it's worth mentioning that, yeah, the efficiency is low, as I mentioned, but we need to consider the huge amount of energy production and how cheap is this. The heat exchanger is the complicated part. Okay, and the power transferred through heat exchanger is represented by this formula, and see here are the two variables here where gamma represents the heat transfer coefficient of the heat exchanger. It depends on the material also, on the design, and A is the area. You increase the area, it's in the range of 500 to 500 meter. Okay, you increase the area, the cost increase. The type of material used, it's preferable to use titanium, but it's costly compared with aluminium. Okay, especially titanium can handle the salty water in the ocean. Now, to find the location, it's important to search for a location where we have warm water on the surface, deep down water cold are available, which produce in the range of 20 Celsius, but within less than 1,000 meter deep. Otherwise, if it is deeper than this, the cost will be increased sharply, and we may don't find it, we may find it not let me say efficient or effective. Let's solve a few problems. I will start with the problem number 1, question 1, and let's read it and then we solve it together. Now, an outage is to deliver 100 mega to the bus bar. This is the final. And warm water comes from solar heated pond that is kept 33 Celsius. The water exhausted from a heat exchanger is returned to this same pond at the temperature 31, so we lose around 2. Okay, 2 degrees. To re-establish the operating temperature, the pond must absorb heat from the sun. Okay, assume an average day and night insolation in watt per square meter is 250, and 80% absorption of solar energy by the water. So we lose 20% of 250, mean we lose 50. So at the end, 200. So yeah, 200 watt per square meter. For cold water, it's pumped from by pipes from down with temperature 8. Okay, there is figure seem to be in the question. It's referred to figure. I will see the figure in the next slide. The warm water lose 1.8 around 2 degree. Okay, while the cold water delta T is 1.35. Okay, 80% of the remaining temperature difference appear across the turbine, and that the rest is equally distributed as temperature differential between the colder side of the warm heat exchanger and the turbine inlet between the warmer side of the cold heat exchanger. Okay. Now what he wants me to do, he wants me to design it and find these variables, the warm and the cold heat exchanger, water flow rate. Now have a look. First of all, he told me that the pumps will consume after internal power pumped and other ends at 40. Efficiency of turbine, he told me 90. And he asked me to find the flow rate for the warm and cold, as I mentioned. And also, he asked me about the area of the surface of the system, of the heat exchanger. And also, he asked me about how deep is, and also he asked me about what deep must the system have. Okay. Now here we summarize from the previous example question and the figure the temperatures for warm and at heat exchanger on the ammonia side and at the cold water. You see here the values, so we can find the differences between them. Okay. Now the efficiency is given 90% for the system, and he told me that in the question that 140 megawatt is the output, so I can divide 140 over 0.9. It gives me the total. This is the total mechanical power extracted from the input. Now if I divide, let me find first efficiency, Carnot efficiency. Okay, Carnot efficiency is delta T, the differences between heat exchanger ammonia temperature divided by the hot with plus 273. It gives me around 5.7%. Now if I divide the mechanical power here produced divided by Carnot efficiency, it tells me how much the heat energy I got from megawatt power I got from the surface of the water. I need it because I want to calculate the flow rate of the warm water. So I divide it by heat capacity times delta T, which is taken from the difference between here and here. It's also given in the question. This is flow rate for warm water. For cold water, I need to know the cold water flow rate. So since the thermal energy here extracted minus the output from the system mechanical, it gives me how much is the rejection energy power rejected from, or energy rejected from the at the condensing side, okay, by the cooling. So if I divide it by heat capacity by delta T for the cold part, I got the flow rate. So these are the flow rate for warm and for the cold water. Now the bond must raise temperature, okay. This is the flow rate, okay, by 2 Celsius, 2 Kelvin, or 2 temperature, 2 degrees, let me say, or 2 Kelvin. Then the thermal power will be flow rate times heat capacity times 2. This is how much the power. Okay. Now he told me the insulation is 250 watt per square meter, and 20% is observed, is lost. So 80% because observed. So 20.2 by 250 is being 50. Subtracted from 250, it gives me 200. So 200 is the total insulation. If I divide the thermal power, okay, in watt, by the insulation watt per square meter, cancel what with what is left square meter. This is the area. For the depth, I will find the volume of the water. If I assume that the depth D and the area A, okay, then V, the volume, is the flow rate times the 3 days. He told me in the question it's calculated for 3 days. They need to be converted into seconds per day. So I multiply by this number, would represent number of seconds per day. So when we cancel, what is left is the volume in cubic meter. Since I have the area, volume divided by area, it gives me how deep I need to go in this pond. Another question, he asked me about the Gulf Stream flow at a rate of this is the flow rate of the water. Its water have temperature 25. Make a rough estimate of the area of the ocean that collects enough solar energy to permit this flow. Okay. This is the flow, okay. Per day, I convert it per second. As you know, we need to work on IS unit system. He didn't tell me about the insulation, so I will assume the insulation. Let's assume it's 250, okay. And he didn't tell me about the temperature, the cold temperature, okay. He told me only the warm temperature. So I will ask him the cold temperature to be 5. So I go 20 difference, temperature difference delta T will be 20. Now the area could be calculated as follow. Flow rate, as you can see, we have it. Okay. The heat capacity is constant given in the question usually, or in the tables available. Delta T, and I divide it by the insulation. When we cancel all these, what is left is the area in square meter. I will stop here to be continue in the next session. Thank you.